Okay, 12.6. This is a little review on related rates. I think we maybe hinted at it here and there. Probably saw some on the first practice test, but this might be a good refresher. We're going to just do a couple free response problems, and this is an assignment. And then you can turn in. So generally, these related rates are pretty wordy. Maybe there's a picture. If not, maybe drawing a picture would be a good deal. Often we're using geometry related area of volume, Pythagorean theorem, trig relationships to connect everything together. Related rates means that there's multiple rates happening at the same time and they are, dependent on each other. You usually are given a rate and then asked to find another rate. But before that, you have to establish a relationship. So ship A is traveling due west. That means this way, but there's also a little compass rose up there toward Lighthouse Rock, just in case that wasn't clear, at 15 kilometers per hour. So I'm going to put that there. So I usually like to draw arrows showing the movement of things, the rates, and then put their value on there. Ship B is traveling due north at 10 kilometers per hour. So you want to have a nice picture for these. Let X be the distance between ship A and Lighthouse Rock. Okay, let Y be the distance between ship B and Lighthouse Rock, time T. Find the distance in kilometers between ship A and ship B when X equals 4 and Y equals 3. And they want to know what this is. So we could give it a variable if you want. We could call it Z or whatever. But it might be good to, if you can create a variable, create it in the picture so that your work makes sense. So it'd be x squared plus y squared equals z squared. 4 squared plus 3 squared equals z squared. Grab another pen. Let's see. So 16 plus 9 equals z squared, 25. And then we're going to take the square root of both sides, plus or minus, and it is going to be positive because it's the distance, and the units are kilometers. Probably want to put units. So that didn't involve any calculus. But what they're doing here is they're probably helping you find something that you're going to need for a later part. Now, I'd say on more modern day first response questions, they're not full-blown first response questions beginning and end. It's usually like part of another problem. They throw in a little related rates on. So B, find the rate of change in kilometers per hour of the distance between the two ships when X equals 4 and Y equals 3. So rate of change of the distance between the ships. According to the variable I've chosen and written in my picture, we're looking for dz dt when X equals 4 and Y equals 3. So we need a relationship between Z and X and Y. By the way, we have some rates here, so now might be a good time to figure out, well, what are those rates? When the ship is moving, X is also changing by the same amount. So this is dx dt. Is it positive or negative? This is one of the big deals with the related rates. They're not going to tell you positive or negative. They're going to use words like increasing, decreasing, inflating, deflating, leaking, filling. And you have to realize where the negative is. Now, you also, in this case, have to realize, well, ship A is moving to the left. That doesn't make its rate negative. But X is getting smaller as ship A gets closer to Lighthouse Rock. So this has to be a negative rate as far as being applied to X. This up here, this is going to be dy dt. And it's going to be positive, not because this guy's moving up, but because Y is getting bigger. If Y was down here and the ship B was moving down, it would still be positive. So it has nothing to do with the direction of the ships. It has to do with what's happening to X or Y. Now, with that in mind, sometimes we can get a rough guess as to what we think is happening with Z. Is Z getting longer? Like if they're both coming in, Z would be getting shorter. If they're both going out, Z would be getting longer. But one's coming in, one's going out. The one coming in is coming in faster, though. So I kind of think that Z might be getting shorter. That's my guess. But a lot of times, It's more obvious than that. But now what we need is we need a way to relate dx dt, dy dt, and dz dt. Before that, we need a relationship for x, y, and z without derivatives. And we already used that relationship on part A. So we write that down. That's one of the big first steps. Get a relationship that relates the different quantities together that are going to be changing, but without the change yet. Then we take the derivative of this implicitly with respect to time. It's implicit because there are no t's. So derivative of x squared isn't just 2x to the first power. You have a dx dt because x is actually some function of time. So you need to follow it up with a dx dt. It's chain rule plus 2y dy dt equals 2z dz dt. Now, before we start taking these derivatives, if any of these values were constant, I'd plug them in first because derivatives of constants are 0 and it makes the work a lot less messy. But we cannot plug x equals 4 or y equals 3 in yet. Those are just the values at the instant we're interested in, but their x and y are changing. So we're looking for this, which hopefully shows up in your work. You know this, which hopefully shows up in your work because they gave them to you. We have x is 4, dx dt is negative 15 plus 2 times y is 3, dy dt is positive 10. So I make a habit of writing pluses and minuses in front of all the rates in my pictures, in my work, when I substitute it. This is what we found on part A. So they kind of let us find something we're going to need on part B. And so this is going to be 60 negative 120 plus 60 equals 10 dz dt. And that's negative 60. And then we divide by 10. We get dz dt equals negative 6. The units, what are the units? Change in z, which is a length, kilometers, over change in time, which is hours. So that is our rate of the distance between them. It's negative, so that means it's decreasing. If I said decreasing, I would not put the negative with the word decreasing at the same time. It's like a double negative. Part C says, let theta be the angle shown in the figure right here, right? Find the rate of change of theta in radians per hour when x equals 4 and y equals 3. So they're asking for d theta dt when x equals 4 and y equals 3 in radians per hour, which is what we would have assumed anyways were the units. So in general, angles on the AP Calculus test will always be radians, not degrees. So we need a relationship between theta, x, y, or z could be brought in. Now I'm going to lean towards not using z just in case I never had done parts A or B, because otherwise I'm going to have to do all that work if I want to use z. Also, what if I mess z up? What if I got stuck on it? What if it gave me just kind of an ugly answer? Even if it was correct, it'd be harder to work with. I would prefer to use x and y. So what we want to use is a basic trig. Sine, cosine, or tangent. Any of them will work. But I'm going to go with tangent. Theta equals opposite over adjacent. The reason I'm doing that is because I prefer to use y and x and dy, dx, dy dt, and dx dt. Now, the derivative tangent is a little uglier than the derivative sine or cosine, so you might choose to do something else. Now we got to take the derivative of this implicitly. Derivative tangent is secant squared theta, d theta dt. That's that chain rule, implicit, which you should get a d theta dt because that's what you're trying to find. Over here, we're going to do quotient rule, low d high minus high d low all over low squared. Now we have xy, x squared, dy dt, dx dt. The one thing we don't have yet is whatever secant theta is, but I'm going to plug these other values in right now. So x is 4, dy dt is positive 10, minus y is 3, dx dt is negative 15. By the way, we definitely expect d theta dt to be positive. It's for sure getting bigger because this moves in and that moves out, the angle gets bigger and bigger and bigger, right? So we should get a positive answer. That's always a good thing to think about up front. So if you don't get one, maybe you'll catch your little mistake. All over x squared, which is 4 squared. Now, secant theta, I would think of as 1 over cosine theta squared. We don't have theta, but cosine theta is adjacent over hypotenuse in a right triangle. And we have the right triangle that goes with theta. So it's going to be 4 over 5. So this is going to be 1 over 4 over 5 squared, which is going to give you 25 over 16. So 25 over 16 is in front here. Now to get rid of it, I'm going to multiply both sides by the reciprocal, and you're going to get a 16 over 25 on both sides to cancel that out. So now let's see what we got. We got 40 plus 45 over 16 times 16 over 25. 16s cancel out. Now, one of the things that you might consider doing on the AP test for your response is leaving your answers unsimplified, because you should still receive full credit. And some of you guys, when you take it further, do make mistakes when you simplify. So either one of these, radians per hour. And it came out positive like we thought it should. So point-wise on this problem, this was 1, 4, 4. Like I said, it's pretty unusual to have a problem that's so related rates focused. Usually now it's just a part of a free response question. And it shows up on usually several multiple choice questions, but usually not so many layers to it on multiple choice, probably just like one of these things. But, 1 point for part A, because that wasn't even calculus. They were just kind of almost helping you out. On part B, they gave you 1 point for setting up the relationship. They gave you 2 points for doing the implicit differentiation correct. And then they gave you 1 point for the final answer being correct. And again, over here, they gave you 1 point for setting up the relationship that brought everything together. And they gave you 2 points for doing the implicit differentiation correct, and 1 point for the final answer being correct. So you get a lot of points. Even if you do mess up this algebra later on, it's not going to be a lot of points. Most of the points are up front, the calculus stuff. After that, we're just substituting and simplifying. That's not really calculus level work. But let's look at the one on the back. And so we have a container. So I picked this one on purpose because this is a very typical kind of problem that has some special tricks in it that could help. Cones specifically come up a lot, but they also are kind of crazy, and there's some ways to make them easier. Container has the shape of an open right circular cone, as shown in the figure above. The height of the container is 10 centimeters. The diameter is 10 centimeters. Water is in the container is evaporating, so it's kind of going away up in the air. So its depth is changing. So its depth is h. And they're giving you dH dt right here. And it's negative because, of course, we're losing water as it evaporates. I'm actually surprised that they gave the negative. Usually they would say the depth h is decreasing at a rate of 3/10 without the negative, but the word decreasing would imply the negative. So we have a bunch of information here. The volume of the cone, height h, so they're giving you the formula for the volume of cone, which is nice, so you don't have to remember that. And part A says find the volume of the cone, find the volume water in the container when h equals 5, indicate units of measure, which some of you guys are losing points for on your last practice test. So 1, remember to put them, but also make sure you know what the unit should be. It's volume. It should be some cubic units. Now, they only gave you h equals 5, and we need a radius. And here's the radius. So here's the deal. We definitely have to establish a relationship between r and h so that we can find the radius from the height or the height from the radius. But also, it's going to help us find DHDTs and DRDTs. But what would be better is to use that relationship right at the beginning of the problem. I don't know if you remember this, and recreate your volume formula in terms of one variable. That'll make the work way easier, like way easier. So the basic idea here is that we get right triangles. You have your R over your H in general. You have an R and an H, which are changing, but up here, this one is 5 over 10. So we could say what we get is we get similar triangles, and corresponding sides of similar shapes have to be proportional. So that means that R over 5 has to equal H over 10, or there's lots of ways you could say R over H equals 5 over 10. These all are going to give you the same relationship in the end, but you just have to be consistent. If you do this over this, you got to do this over this, or you do this over this and this over this. Anyways, from here, you should decide, well, is it going to be better to get this equation in terms of all R or all H? The fact that they gave you DHDT probably means you're going to want all H. Or if they're asking you specifically about finding DHDT, then you want all H. If they give you DRDT or ask you for DRDT, probably want all R. So we're going to go ahead and I think try and get all H. So that would be R equals 1/2 H. And so we're going to plug that into our volume formula right now because we could use it on part A. So we plug in 1/2 H in for R, which gets squared. The 1/2 gets squared. So it's going to be pi over 12 H squared. That's our new volume formula. And so when H equals 5, so this is our new volume formula we're going to use for everything, hopefully. When H equals 5, we don't have to find R anymore. We just plug it directly in, and we get our answer, 125 pi over 12. The units are cubic centimeters. Okay? Now, point breakdown here, 1 point, 5 points, 2 points, and then the units make up their own point, which sometimes they do that. Instead of dinging you every time for the units throughout the problem, if you mess up once, you just lose 1 point, and then you can't lose it again. No calculus, really. That's geometry, and but it's going to help us with our calculus. Find the rate of change of the volume of the water. So we're looking for dVdt when H equals 5, indicate the units of measure. Now, I'm always going to put units of measure, even if they don't ask me, because I don't want to miss it. Now, if they don't give you any specific kind of units, I'm not going to write generic units. Okay, so anyways, we need a relationship between V and probably H. And hey, what do you know? We got it. We got volume equals pi over 12 H squared. And then we're going to take the derivative of it with respect to time. It's going to be pi over 6 H dH dt. Remember, people love to forget that implicit extra dH dt, but then that information they gave you at the top is going to be wasted, and that's going to seem kind of weird. Now, do we expect the volume to come out, the dVdt to come out negative or positive? If it comes out negative, that means we're losing volume, which is what is happening. So we should get a negative answer, by the way, right? That's always a good thing to maybe think about before you get too far, so you can catch mistakes. So now, we'll go ahead and plug 5 in for H, and then dH dt when H equals 5 it's actually constant. So it's always negative 3/10 for dH dt. So we're going to get negative pi over 4. Shoot, I messed something up. What did I mess up? Oh. Yeah. Okay, yeah, I messed up right here. In fact, no, I got that one right. Okay. This should be h cubed, by the way, right? Yeah, I did mess up. That should be h cubed. There's an h squared here and another h. So that should be h cubed. I wrote the right thing down, maybe because I was cheating, I guess. So this should be cubed. And so this is going to be pi over 4h squared. It's going to be pi over 4h squared. So it's going to be 25 over 10. You can reduce it. I'm just going to rewrite this because it's so messy now. Pi over 4, 5 squared, negative 3/10. So that's 25. 5 goes into that. 5 goes into that. And then we could rewrite it negative 15 pi over 8. Units are cubic centimeters. It's change in volume on top over change in time on the bottom. The time on this problem is, just look around for it, hours. So that's what we need. Now, point-wise, that was 5 points. And 1 point was actually developing this relationship that I started on part A. So that was a point. On part A, this answer right here was a point. And then here, the derivative with respect to time implicitly was 2 points before you even plugged anything in. And then another point for your final answer. Okay, C. Now, C is kind of weird, but it's only 2 points. So we're not going to worry too much about it. By the way, your units for both of these are a point. If you mess one up, you lose that whole point. C says, show that the rate of change of the volume of the water in the container due to evaporation, that whole long thing, the rate of change of the volume in the water in the container due to evaporation, that's dVdt, equals directly proportional. So that's what a lot of times we use like a K for direct proportionality. Directly proportional. It's like a linear relationship. It's just y equals x times some number, the same number all the time. Directly proportional to the exposed surface area of the water. And then what is the constant of proportionality? So we're trying to show that this happens. Now, usually in these like fluid problems, when they talk about surface area, they actually mean the actual surface area, the top surface. Whereas in geometry, surface area is often the area around the whole shape, which could show up on some problems too. Well, what is surface area? Well, the surface area, it's a circle. It's pi r squared, right? So that means we want to somehow show that dV dt has a pi r squared in it, and then just some number. All right. So now we kind of know our goal. Now, for dV dt to end up with an r squared, we probably want the volume formula in terms of pure r. We could work with h right now, and then we're going to have to change it to r, which is probably harder to do later. So instead, I'm going to use r over h equals 5 over 10, and I'm going to get h equals 2r. And I'm going to rewrite my volume equation 1/3 pi r squared h, and I'm going to plug 2r in there. So I'm going to get 2 pi r cubed over 3. I just think that's going to be easier. Now, so let's see. I can show you the other way. And the other way is if the surface area is pi r squared, then we can say, well, r is 1/2 h. So really, we're also looking for possibly pi over 4h squared. If you can get that, that's also surface area. So you could do it like that if you want, or you could start this over. Okay, so then we're going to take the derivative with respect to time, and we're going to get 2 pi r squared dr dt. All right? The 3 power rule cancels that 3, decrease it by 1, so you still have 2 pi. Those are just numbers. Here's your pi r squared. Okay, that must mean the other stuff is your number. And dr dt, it says, well, then we run into a new problem. We don't have dr dt. So we go, well, if r equals 1/2 h, then dr dt equals 1/2 dH dt. And dH dt was the rate they gave you at the beginning, which was negative 3/10. So that's going to be negative 3/20. Right? So then we could rewrite this dV dt equals negative 3/10 if I multiply those together, pi r squared. So now I think we've shown that it's a number times the surface area, which was part of the challenge. And then the other one was to find the constant of proportionality. So the constant of proportionality is the thing that I used a K for, which is common. You could use a different letter if you want. It's pretty much like a slope. Constant of proportionality is negative 3/10. By the way, yeah. So, if you did it the other way, like I said, I mean, that might have some benefits. If you use the volume equals pi over 12 h cubed, then you could do dV dt equals pi over 4h squared dH dt, and then you can say, oh, there's that pi over squared dH dt. Cool. That's the surface area, and then dH dt is negative 3/10. That's the K. That's the constant proportionality. So that would also work. But anyways, okay, that's it. If you paid attention here, then you got an assignment done in less than 30 minutes, and that's the assignment for today. Okay.